Chapter 7, Concurrent and Parallel Forces. This lecture will help you understand how to find the vector sum of concurrent forces. First, we'll look at a list of forces that we'll be working with in this course. The gravitational pull of the Earth on an object on or near the surface of the Earth is called weight. The agent for the weight forces is the entire Earth pulling on an object. An object's weight vector always points vertically downward, no matter how the object is moving. Springs come in many forms. When deflected, they push or pull with a spring force. When a string or rope or wire pulls on an object, it exerts a contact force that we call tension. The direction of the tension force is always in the direction of the string or rope. The force exerted on an object that is pressing against a surface is in a direction perpendicular to the surface. We call this the normal force. At a microscopic level, we can think of atoms attached together by small springs, and the weight of an object compresses the springs, causing the springs to exert a backwards push. The normal force is responsible for the solidness of solids. The surface pushes outward against the bottom of the skis. The normal force is always perpendicular to the surface. The symbol for the normal force is N. Friction, like the normal force, is exerted by a surface. The frictional force is always parallel to the surface. Kinetic friction, denoted by F sub k, acts as an object slides across a surface. Kinetic friction is a force that always opposes the motion. Static friction, denoted by F sub s, is the force that keeps an object stuck on a surface and prevents its motion relative to the surface. Static friction points in the direction necessary to prevent motion. Static friction is always greater than kinetic friction. It is easier to keep an object moving than to start an object moving. In the figure at left, the motion is to the right. The direction of kinetic friction is always opposite the direction of motion, and therefore to the left. In the figure at right, the crate is not moving. The woman is pulling to the left. The direction of static friction is opposite the direction the crate would move if it were allowed to move, and must point to the right. The force of a fluid, like air or water, on a moving object is called drag. Like kinetic friction, drag points opposite the direction of motion. You can neglect air resistance in all problems unless a problem explicitly asks you to include it. Thrust is a force that occurs when a jet or rocket engine expels gas molecules at high speed. Thrust is a force opposite the direction in which the exhaust gas is expelled. Concurrent forces are those forces that are applied or act at the same point on an object. The resultant force is the sum of two or more forces acting at the same point on an object. The resultant force is found like that of any other vector quantities we have analyzed so far. If necessary, review vectors in standard position and vector tables. Concurrent forces are forces whose line of action all pass through a common point. The figure shows four forces all acting on an object, and they all act on a common point, the center of the object. This figure shows three forces all acting on a single point labeled X. The rock is resting on the side of a slope. There are three forces acting on the rock: gravity, which points towards the center of the Earth, down; the normal force, which is perpendicular to the slope; and the frictional force, which points uphill, parallel to the hill. But in the opposite direction the rock would roll if it were allowed to roll. When two or more forces act at the same point, the resultant force is the sum of the forces applied at that point. The resultant force is the single force that has the same effect as two or more forces acting together. Here the resultant force R is the vector sum of the two vectors v and w. The two vectors are adding using the tip-to-tail method. The tail of vector w is placed at the tip of vector v. In the parallelogram method of vector addition, the sum is obtained by constructing the parallelogram using the two vectors as adjacent sides and then constructing the opposite sides parallel as shown in the figure. The diagonal of the parallelogram is the resultant, or sum of the two vectors. In the figure, two people on opposite banks are pulling a boat up a small river. Note that the effort forces must be equal to keep the boat in the middle of the river. The direction of the equal effort forces is along the ropes, and the direction of the resultant force R is upriver. What would happen if the effort forces were not equal? In Chapter 3, we discuss how to obtain the correct angle of a vector. We first calculate the helper angle, alpha, which is the inverse tangent of the absolute value of the y component of the vector divided by the x component of the vector. We identify the quadrant by the signs of the x and y components. We obtain the angle theta in standard notation as shown in the figure. Two workers move a crate by applying two ropes at the same point. The first worker applies a force of 525 newtons due north, while the second applies a force of 763 newtons due east. Find the resultant force, F sub r, and its standard angle, theta. We define the direction north as the y-axis and the direction east as the x direction. Force F sub 1 points due north, so the x component is 0, and the y component is 525 newtons. Force F sub 2 points due east, so the x component is 763 newtons, and the y component is 0. The net force is the sum of the x and y components, given 763 newtons east and 525 newtons north. Since both components are positive, the net force is in the first quadrant. The standard angle is equal to the helper angle and is equal to 34.5 degrees. The magnitude of the net force is the square root of the sum of the squares of the components and is equal to 926 newtons. The figure shows the resultant force. Two workers move a large crate by applying two ropes at the same point. The first worker applies a force of 525 newtons at an angle of 40 degrees north of east, while the second worker applies a force of 763 newtons due east. Find the resultant force vector. To begin, we must find the x and y components of F sub 1 and F sub 2. Assign x as east and y as north. Since F sub 1 is 40 degrees north of east, the x component of F sub 1 is 525 newtons times the cosine of 40 degrees, which equals 402 newtons. The y component is 525 newtons times the sine of 40 degrees, which is 337 newtons. F sub 2 points due east, so the x component is 763 newtons, and the y component is 0. The sum of the x and y components are 1,165 newtons and 337 newtons, respectively. Since both components are positive, the vector is in the first quadrant. The angle is 16.1 degrees. The magnitude of the force is 1,210 newtons. Three forces are applied at the same point on an object. F sub 1 is 375 newtons east. F sub 2 is 575 newtons, 60 degrees north of east. and F sub 3 is 975 newtons, 80 degrees west of F sub 2. Find the resultant vector. By the way, if the object were 50 kilograms, can you determine the acceleration of this object? Which of Newton's laws would you use to determine this? We must find the x and y components of each vector. The x component of F sub 1 is 375 newtons, and the y component is 0. The x component of F sub 2 is 288 newtons, and the y component is 498 newtons. Since the angle 80 degrees is measured from F2, we must add 60 degrees to find the standard angle of F3, which is 140 degrees. This gives minus 747 newtons for the x component and 627 newtons for the y component. We notice that vector F3 is in the second quadrant and that the x component must be negative. We sum the x components and get the x component of the net force as minus 84 newtons. The sum of the y components gives the y component of the net force as 1,125 newtons. Since x is negative and y is positive, the vector is in the second quadrant. The standard angle is 180 degrees minus the helper angle, or 94 degrees. The Pythagorean theorem gives the magnitude of the resultant vector, or 1,130 newtons. Newton's second law relates the acceleration and the force. Dividing the net force by the mass gives 22.6 meters per second squared.